Welcome to the workshop. We want to continue taking a look at section 3.7, conditional distributions. And we want to look at the situation where we are looking at joint density functions, so continuous random variables in this case. And one of the things that we need to really have a good understanding of in order to understand what we're looking at when we consider the continuous random variables is the joint densities as well as the marginal densities. So we'll give the definition here at first, and then we'll take a look at an example, and we'll go ahead and use Mathematica to help us visualize what's going on. Again, what we're looking at when we take a look at marginal densities, because that's really going to be where we understand how the continuous variable case, the continuous random variable case, is very similar to the discrete random variable case. Okay, so let's take a look at our notes. So for a conditional density, if f of xy is the value of the joint density of the continuous random variables x and y, and h of y is the value of the marginal density of y at x, then the function given by f of x given y rather, is equal to f of x y divided by h of y, of course, where h of y is not equal to 0. So when we're taking a look at this, one thing that's different about the joint probability distributions versus the joint densities is that, or densities versus distributions in general, is that the densities, when we choose a particular value, it's not giving us a probability in and of itself, whereas in the distributions, it is. To get the density, or to get the probability from a density function, requires us to find the area below the density function. So we have to integrate. So when we represent our conditional probabilities, what we want, right? We're not going to simply have a probability divided by a probability. What we're going to end up with is, right, we would have to integrate this function to get a probability, and then we would have to integrate this function to get a probability, and then we would divide those two probabilities. So it seems a little bit weird because the integral of a quotient is not the same thing as the quotient of the integrals necessarily. So it seems a little bit weird for us to do this, but this is in fact how it does work out. This is what we want, and we'll take a look at that a little bit more when we are considering our next example. Okay, we'll take a nice visualization, and to be honest, the textbook actually has a really good visualization for conditional densities as well. So I would certainly encourage you to do as I'm expecting you to do anyway, and that is look at the textbook. All right. So this is the marginal density of x given y. Of course, we can have the marginal density of y given x, which we again give the name w, represent the function with w, y given x. And of course, it's still f of x comma y, but in this case, divided by the marginal distribution, marginal density rather, of x. So, and we want g of x not equal to 0 here. So again, that's the conditional density of y given x. So for our example, what we'd like to do is rely on the fact that we've already calculated a marginal density for a function, and so we're going to revisit that same function. In the previous section, we considered the marginal density of this function. In particular, we found the marginal density of x. So in example 3.6.3, we found the marginal density g of x, which is 2 times x times e to the negative x squared for x greater than 0, and it is 0 otherwise. All right, so this is what we want to revisit. And because we're considering the same function, what I'd like to do is I'd like to take a look at Mathematica to help us get this visualization. So I've already plotted for us the density, the joint density. Okay, so we have x and y and z. And when we talk about the marginal density, essentially, like I said, what we're doing is we're considering what's going on from this side view. But we are also considering, you know, what each slice of this has. So when we consider the marginal density, what we're getting is we're getting slices. Each value of the marginal density is actually giving us a slice of this thing. So what is it? What do I mean? What does it look like to be a slice? Well, let's take a look at a small range of values for x. For example, since we're looking at inputs of x. So I'm going to take a value of that's about a tenth thick, so that way it's relatively thin overall. So let's say our x values are between 0.5 and 0.6, 5/10 and 6/10. So if I do that, and I let it think about this for a moment, what it's going to give us is it's going to give us a slice. It won't be a thickness of 0, it's a thickness of 1/10, so it's not perfect. But this is the idea. So what I'm doing is I'm just looking at this slice, but it's not just the slice from the side view here, right? What it is it has its depth as well. So we're taking on we're considering all of this additional stuff that's going on there. But when we restrict ourselves to one particular x value, when we do that, we're looking at just a slice. So what does it mean for us to consider a probability on that slice? Well, we are reducing ourselves to a function of one variable, y. And when we have a density function for just y, it is exactly just we're looking at the area under a curve. And so what we're looking at here when we talk about the marginal, when we talk about the conditional distribution of y, right, we're looking at thinking of this as a flat, 0 thickness plane. We're looking at the area underneath this curve. Okay, so the total area under that curve is given by g of x, because that's what g of x represents. It represents the area in that slice. So that way, when we integrate over various x values, what we get is the total area underneath the 3-dimensional object. Okay, so if I wanted to find the probability that, like the marginal probability that x is between 0 and 1, for example, if I wanted to do that, I can do that. And what that is it's the area of this solid object here. Okay, or the volume of that rather. Okay. But again, what I'm interested in is one particular value of g of x, giving me the area of one of those slices. Okay, so hopefully you follow along with that. Of course, the book presents that similar explanation of the conditional probability. So then we're just looking at how much of that area, right, a slice is area. So we're just looking at that slice for a particular value of x, and then looking at a range of y values on that particular slice. Okay, so area divided by area, probability divided by probability. So then it makes much more sense that this, right, g of x is the area of that one slice, and then f of x, y, when we integrate over that, we're going to find, right, because essentially all that we would be integrating over is the variable y, So it's no longer a function of x when we perform our integration. So then it makes sense that the integral of a function divided by function is the integral of, well, the x's are just constants, so all that gets pulled out. G of x in particular would be pulled out as 1 over g of x. Okay, so it actually makes sense for us to do this. Anyway, so let's move on. If we want to just try the computation and maybe that will provide a little bit of explanation, we can do that. So let's complete this example. So we already found the marginal distribution of x. So if we want to find w of y given x, this is an example where we're not considering a specific value of x. We would have to plug that in order to determine where our conditional probability is being evaluated at. So this would be f of x comma y divided by g of x. Of course, we don't want division by 0, so we're only considering x values that are greater than 0. And we have f of xy, and we have g of x. So this is for x greater than 0, this is for x and y greater than 0. So it's still going to be split into two pieces where x and y are greater than 0. And it will be 4xy times e to the negative x squared plus y squared, f of xy divided by g of x, which is 2 times x times e to the negative x squared. And this is for x greater than 0 and y greater than 0. And we do still have the ability to say what this conditional probability is for values of y that are less than or equal to 0. But again, this is undefined where g of x is 0. So we don't want to consider x values less than or equal to 0. So this would be for y less than or equal to 0. And how do we handle this conditional probability where x is less than or equal to 0? Well, again, g of x is 0 there, so we would have division by 0, so it's undefined. So we don't include any comment about it. It is undefined. We didn't define it. Okay. This can be simplified, so we should go ahead and do that. And that's going to give us that the conditional distribution of y given x is equal to 2 and the 4 reduce, the x and the x cancel, and then the e to the powers, right? I can go ahead and simplify that. So I'm going to lose the x squareds in the numerator, and the denominator is going to go away. So I'm just left with 2y e to the negative y squared for x greater than 0 and y greater than 0, and it's 0 for y less than or equal to 0. So it's a little bit weird that what we end up with actually doesn't depend on x at all. So that's kind of fun. All right, but that is exactly what we were looking for. So that's all that I have to share for this video. Maybe I should include one last comment. Once we choose a value of x, then that would give the particular distribution, the particular conditional distribution. But in general, we can express the conditional distributions in terms of x and y. And we'll see a little bit of that in our last example. Not our last example, the next example. Yeah, that's what we'll see. All right, so anyway, thank you for your time and attention. I'll see you guys back in the workshop very shortly for more on conditional distributions.